Okay, so let's get started. So last time we were actually trying to do these plane monochromatic waves. So we started with this Maxwell's equations, and one of the most important applications of Maxwell's equations are electromagnetic waves. And that displacement term is responsible for electromagnetic waves. So these plane monochromatic waves are simple solutions of Maxwell's equations in absence of charges and currents. So these are solutions of Maxwell's equations in vacuum. So let me start. So you have, these are the let me use a thinner pen. So these are the Maxwell's equations in vacuum. These are the divergence equation, and then there are curl equations. This and del cross B equals 1 by C dou E dou T. So these are the Maxwell's equations in absence of currents and charges. Let's do one thing. If we take a del cross of this third equation, we have del cross E is equal to minus 1 by C dou T of del cross B. And so del cross E is, so let's just do the right hand side first. So this is just del cross B is 1 by C dou E dou T. So this is 1 by C squared dou 2 dou T squared E, and the left hand side is del cross E, which is nothing but del squared E. So there's also a del dot E term, but since del dot E is 0, that term goes to 0. So del cross E is so del cross E is, so this is just a vector identity. So let me actually see what this identity is. Give me a sec. So right, so del cross, okay. Okay, so I did del cross of this, del cross E is equal to, from vector identity, this is equal to gradient of del dot E minus del squared E. So we get minus del square E here, and there is a minus. Okay, so there's a minus sign here. So del cross B, yes. So basically you have this equation, right? So this is a wave equation. So a wave equation, right? And so you recall, like even for sound waves or like any simple waves, you have equations like dou 2 by dou T squared psi equals C squared dou 2 dou X squared psi. So this is the simplest wave equation, and this is of that form, except that E is a vector, and here the simple example has a scalar, and this is del squared, and this is 1D version of that. So let's see. So this is like the general. So this equation is valid, and you can write a similar equation in terms of B. It will be the same equation. So basically, what it means is that both E vector and B vector satisfies this wave equation. Okay, right, and one of the special forms of this wave equation are plane monochromatic waves. So what do I mean by plane monochromatic waves? What I mean is that I can write my E as E naught e to the I k dot x minus omega t, right? So this is the phase factor. The e to the I factor is the phase factor, and right. So this is a constant. So this is a plane waveform. So this is a plane waveform for any perturbation. Okay, and similarly, we have v, and this E naught is actually a vector. Right, the time and space has been absorbed in this E to the I, and this can also have a phase. So E naught in general, even this guy, can be complex. And right, so it has X, Y, Z, 3 components in principle. Similarly, B has a similar form. Okay, but all the spatial and time dependent is in this e to the I factor. Okay, so these are plane wave solutions. So let's see. Now the nice thing about this form is that if you do dou dot t of anything which is in this form, this goes to minus I omega, right? If you do a partial by partial t of this, it just pulls out minus I omega in this expression. Similarly, the gradient actually just pulls out ik. So a lot of these del crosses and partial by partial t's become very simple. So let's look at this equation. So this, right? So right. So let's look at del dot b. Del dot b is equal to what is del dot b? So if I do del dot of this, all it does is it pulls out ik dot b, right? If I do a del dot of this, all it does is it pulls out ik dot, and this is not b naught, this is b, because it has both b naught e to the ik. So basically this is equal to 0, right? And similarly ik dot e is equal to 0, right? And the interpretation of this form is that you have some propagation direction k. Okay, so the waves are propagating in this direction, and in fact these are like infinite plane waves. So the phases of the wave are sort of changing in this direction, and these are sort of the wave fronts. Nothing varies along these wave front directions, and these are the wave fronts. Okay, wave fronts have a constant phase. Okay, right. So basically what it tells us is that these waves are transverse, right? Basically the fields E and B are perpendicular to K. Okay, the direction of propagation. So okay, this is good. And now if we look at this equation number 3, we get ik cross E is equal to minus 1 by C minus iota omega B. So this is the relationship between E and B. So K cross E equals omega by C times B, right? In fact, if you look at this equation, the wave equation, and if you substitute this form, the plane wave form in that, what you get is, so grad square will just give I k squared is equal to 1 by c squared minus I omega squared. Basically, this is omega squared equals k squared c squared. So this is the dispersion relation for plane waves in vacuum. Okay, the relation between the frequency and wave number is called a dispersion relation. So we know that so let's see, so we actually divide it by magnitude of k, so we get omega by ck. In fact, what this means is that omega equals plus minus ck, right? If you take square root on both sides, this is what we get. So what does it mean? So it means k hat cross e, so omega by ck is equal to plus minus 1, right, from this dispersion relation, right? So if we take positively propagating waves, that is, if we take the plus sign, and if we sort of consider our x-axis is along k, or along k, then this is like x hat, this is e, and you know, if x-axis is along k, and if we are choosing omega greater than 0, then we have, you know, so k is along x, and this is sort of like a triad. So you know, and E and B are in the perpendicular plane, of course, right? Because k dot E and k dot B are 0, and k cross E is for a positively propagating light wave. K, so it's like x, y, z. So these are like, this is like a triad, k hat, comma E hat, comma B hat is like a orthogonal triad, like x, y, z. So k is perpendicular to both E and B, and E, I mean, all three are perpendicular to each other, and they are like your x, y, and z hats in the standard Cartesian coordinates. So how do we see that? So if we do E dot of this, right? If you do a E dot of this, you'll see E dot B on the right hand side, and E dot of k cross E is 0 because k cross E is perpendicular to E, right? So this is a, you know, all three are orthogonal and it forms a triad. Okay. Good. So you know this, all of you must already know this, but it's good to sort of repeat. And for such waves, you know, phase velocity, you know, in general for waves, phase velocity is nothing but k hat omega by k, and the group velocity is dou omega dou k, right? So, or right, so these are like usual things for all sorts of waves, all kinds of waves. For the light waves, this is particularly simple. So both v phase and v group are equal to c, and both of them are along k hat. Okay, this is not true in general for a general class of waves. Okay. Okay, what about energy density in waves? Let's see, energy density and flux carried by these EM waves. Let's look at the expression. So you recall E squared by 8 pi is the energy density. Okay, this is nothing but E naught squared. And you know, generally, you know, we are dealing with e to the is, but the convention is that when you want some physical unit, what you do is you just take the real part of this complex number. So your E, for example, the real electric field, which is the real number, is the real part of this complex E, right? So this is the usual thing we do. And the nice thing about e to the I is that if you take derivatives and curls and so on, you don't convert sines into cosines and cosines into sine. It only brings about like a phase factor, and everything is very, the manipulations are very, very easy. So this is like the standard practice that we use when we deal with waves. So what is E squared by, so this is just E naught squared by 8 pi. And then we have, say, cos squared times this phase factor. This whole thing is phi, the phase factor. So basically what you normally do is, these waves are traveling very, very fast. They are oscillating very, very fast. So what you typically do is you average over this fast varying phase. And if you do that, what you get is this is equal to E naught squared by 16 pi, because the average of cos squared phi for a uniformly varying phi is nothing but half. So basically this is the energy in electric field for an EM wave, average energy. Similarly, B squared by 8 pi, which is the magnetic energy for a plane wave in vacuum, this is equal to B naught squared by 16 pi. Okay, now you see from here, where did it go? Yes, you see it from here that the absolute value of E and the absolute value of B are equal, right? Because this is a triad, and this is E naught, E hat, and B hat. So E equals B. So absolute value of E and B are equal. So E naught is equal to B naught. Okay. So the wave energy, or the average wave energy, and this average is almost always implied because the wave sort of oscillates very, very fast, is equal to E naught squared by 8 pi, where E naught is the electric field amplitude, which is equal to the magnetic field amplitude. This is also equal to B naught squared by 8 pi. Okay, and if you recall our Poynting flux S, and we also sort of average this Poynting flux over the fast varying phase factor, what we get is C by 4 pi E cross B, right? So this is equal to C by 4 pi. What was E? So so you see KEB is a triad, so E cross B is K. E hat cross B hat is K hat. So we have E naught squared, and there's also this cos squared phi factor, which will give you a half. So cos squared phi, and then you have K hat or N hat. N hat is the direction when you think in terms of rays, but K hat is the the direction of wave number. So this is what we have, and this is nothing but N hat. N hat and K hat are the same actually, just a slightly different viewpoint. So C by 8 pi E naught squared, right? If you look at the wave energy and this flux, so what we get is flux is N hat times C times wave energy density. This is actually wave energy density, it's per unit volume, right? Because E squared by 8 pi is energy stored in the field per unit volume. So this actually has the right interpretation, right? Energy density times the speed of propagation along the direction of propagation is the flux. So this looks like, this sort of satisfies this E equals PC type of a relation in the photon picture. Okay, good. So this is about plane waves. Any questions? No. Okay. Okay, good. Yeah, this is basic stuff. Is there an audience who has not heard about this material before? Okay, good. That's what I expected. But anyway, okay. So now we will actually go to radiation spectrum. What is meant by radiation spectrum? So normally, in the previous section, we considered this infinite plane wave. But normally, you don't have infinite waves. What you have are wave packets. So, for example, you have a wave which starts from 0 amplitude, and then its sort of amplitude grows, and and it sort of goes back. So you have, in reality, you have things like this, wave packets. So so this is like, say, electric field as a function of time measured at a given place. Okay, so you're waiting. Suppose someone shines light at you, you don't get anything early on, and when the light pulse crosses you, you start seeing these oscillations, and once it passes you, you don't see anything at all. So this is like a wave packet. So you have like a envelope of this wave, and then fast variations. So this is sort of like your frequency of variation, and this is like time period of the wave, and the full duration of the wave packet is like your delta t, right? The pulse width. And typically, like if someone shines light at you, in that case, delta t is much bigger than the time period of the wave, which is nothing but 2 pi by omega naught, right? If omega naught is the frequency of these fast variations, the time period is just this. And if the pulse lasts for a long time, this is typically observed. Now we can actually, so this is in time space, we can actually look at it in Fourier space or in omega space, right? So basically the way to look at it is formally through Fourier transforms, but let me actually tell you. So this is centered at omega naught. So most of the power actually comes in this field, comes at omega naught, this frequency corresponding to the time period of fast variation. But there is also spread in this energy spectrum of this wave, which we call delta omega, right? And this delta omega actually corresponds to this delta t. So this is like this is of order 1 by delta t, right? So we can actually go and see it in terms of plane waves. For example, if you have infinite plane wave, right, omega naught, this energy as a function of omega is a delta function at omega naught, right? An infinite plane wave is a delta function. But if you have a pulse, it has some spread in frequency, delta omega. And in fact, uncertainty like relation, delta omega delta t, right, is greater than 1. Right? So this is called Fourier uncertainty. And this is this is mathematically the same as the Heisenberg's uncertainty principle, right? Because the p space and x space are sort of Fourier transforms of each other. They are related. So if the wave is very, very narrow in frequency, like an infinite monochromatic wave, then it will be very, very broad in time. Okay, so mathematically this is equivalent to the uncertainty principle in quantum mechanics. Okay, so let me, so this is sort of the picture more physically, but I'll actually do it more mathematically, introducing the Fourier transform. So let's get started with that. So this E hat omega is equal to 1 by 2 pi. So this is the Fourier transform of the electric field. So ET e to the I omega t dt. Okay, so if you have some variation of electric field in time, right, you can actually describe this in time space or in the frequency space. They are totally equivalent and they contain the same amount of information. So this is the way to go from real space to frequency space. So this is a Fourier transform. Okay. Now, usually you have the inverse relationship as well. So that's given by this. Sorry, just a sec. D omega. Okay, so this is the inverse Fourier transform. Now, if we substitute this E hat omega here, you will actually see that you will get ET equals, right? Basically, this is because of, I mean, this relation has to be satisfied in order to go from frequency to time space and vice versa. So I hope everyone has done some basics of Fourier transforms, right? Yes, so I'm actually not going to do like show all these things explicitly. I'm assuming that you already know it, right? And there is like useful relationships involving delta functions which help you prove all this. Okay. Okay. So if I mean not if is actually not needed. Just a sec. So is there anyone in the class who does not know basics of Fourier transforms? It's very, very important. If you don't know it, you should brush up at least the simple aspects of it. Okay. Now, if electric field is real, right? It's a real field. So ET star is equal to ET. So the complex conjugate of this electric field is equal to the electric field itself. Now, if we do that here, if we take a complex conjugate, I should not write here, just a sec. I'll write it separately and then do my manipulation. So E star t is equal to minus infinity to infinity E hat omega star. In general, E and E hat are complex numbers, E to the plus I omega t, complex conjugate d omega. So t and omega are real, okay, but E and E hat can be complex. So if E star t is equal to ET, so this is equal to ET, which is equal to minus infinity to infinity E hat omega e to the minus I omega t d omega, right? So, I mean, it's sort of like we can actually do a change of variables. So S equals minus omega. Omega is allowed to be negative, just like time is allowed to be negative. You're waiting from t equals minus infinity to t equals infinity. Okay, so if we do this change of variable, what does this become? It becomes infinity to minus infinity, E hat minus S, e to the I S t ds, right? Is there a minus sign? Right, so that this minus sign just becomes like this if you put the limit from minus infinity to plus. So what you see is that the form of this integral is the same as that, right? And now we can actually this s and omega are really labels. So what you see is this term and this term have to be the same. That is e star e hat star omega equals e star e hat minus omega. So this is because of this reality of the electric field. So this is one useful, this is the relationship between the Fourier coefficients if the signal is real. Okay, so you only have to worry about omega greater than 0. If you get the omega greater than 0 Fourier coefficients, the negative Fourier coefficients can be obtained just by taking the complex conjugate of the omega greater than 0, for example. Okay, good. So this is from this reality condition. Okay, so there is also something called Parseval's theorem. Parseval's theorem, which basically expresses the fact that the energy in the signal, whether measured in real space or in Fourier space, is the same. So mathematically, this is this E t squared t. So this is the energy measured in real space is equal to 2 pi minus infinity to infinity E hat omega square d omega. Right, so the first term is the energy measured in real space. The second is energy measured in Fourier space. And these 2 pi's and so on are really because of this condition that if you substitute this back here, sometimes you'll see 1 over square root of 2 pi here and 1 over square root of 2 pi here. The point is the product should be 1 by 2 pi. In the same way, sometimes you'll see 1 by 2 pi square root here, 1 by 2 pi square root of here. But in the end, they should be consistent. That's the main thing. Okay. So absolute value of E hat omega square is equal to E hat omega times E hat star complex conjugate, right? And this is nothing but right, so this is this, but we know that E hat star omega is equal to E hat, so E hat star omega is equal to E hat minus omega, and so this is the same as this from this equation, and similarly if we put omega equals minus omega here, so we'll have E hat star minus omega, right? That's nothing but E hat square evaluated at minus omega, right? This is E hat square evaluated at plus omega. So what it means is that the Fourier power, so Fourier power same for omega and minus omega. So the negative frequency has the same power as the positive frequency. What you can, using this, what you can do is you can just write if ET is real. So you can write this as 4 pi 0 to infinity E hat omega squared d omega. Basically, you only have to worry about the positive frequencies greater than 0. This is very, very important. Parseval's theorem is one of the most important theorems in Fourier analysis. Useful to know it. Okay, good. Let's see. Now we want to connect all this to we actually want to relate this E squared, obtained through wave and electromagnetic theory to specific intensity, for example. So we have so dW by dt dA is equal to C by 4 pi ET squared. So let me first tell what this is. So this is energy crossing per unit area per unit time, right? This is nothing but Poynting flux. So this is energy crossing per unit area per unit time. This is nothing but C by 4 pi E cross B. E and B are perpendicular. So we are still sort of considering monochromatic plane waves. So you have this relationship. We have not averaged it over the wave phase. Okay. Now this is the Poynting flux, or energy per unit area per unit time. Energy crossing some area per unit area per unit time. Now dW by dA is equal to C by 4 pi minus infinity to infinity E t square dt. Okay. Now this, if we are waiting at some area and integrating it over all times and asking how much energy per unit area crosses it at all times, this is what you will get. Okay. But from Parseval's theorem, we can actually write this in terms of the Fourier space energy. So that's nothing but from here, right? We can write this as C times 0 to infinity E hat omega whole square d omega. Right? This is the energy crossing per unit area. Okay, and we can actually write then, just by comparison, we can write the energy by per unit area, per unit frequency, energy crossing per unit area, per unit frequency as C times E hat omega square. Okay. If you recall our specific intensity, right, so if you recall our specific intensity, that was energy per unit area, per unit time, per unit frequency, and per unit solid angle. Now here we have energy crossing per unit area, per unit frequency, right? Nu and omega are related. So nu is equal to 1 by T, which is equal to omega by 2 pi, right? So nu equals omega by 2 pi. Okay, so this is energy per unit area per unit frequency. But what we want is energy per unit area per unit time per unit frequency. And the solid angle, if you have isotropic for isotropic waves, you can actually replace 1 by d omega by 1 by 4 pi. Okay, so that part we don't have to worry so much about. But what about this 1 by dt? Now, for that, so d omega dt dA d omega is really equal to 1 by t, 1 by this delta t actually. This time duration of the pulse times dW by dA d omega. Okay, now right, so just a sec, let me make some space. Okay. So basically, this is the duration of the pulse. Okay, so we have right from this expression, if you just divide by 1 by delta t, so this is equal to 1 by delta t, c by delta t, c by delta t, e hat omega squared. In the limit, and if you have like if you have a very long pulse in the limit of a long pulse, this just becomes limit delta t going to infinity. If you have like a monochromatic wave which extends from minus infinity to infinity in time, then this is just that. Right. Okay, so now so this is basically your this is sort of like your, what is it? It's sort of solid angle integrated in some sense. So this is your 4 pi times j, right? So there is this mean intensity. So here I'm actually multiplying this by all angles, and this is actually also relative. Now, if you divide it by c, you get the energy density in the wave. I mean, this is like an attempt to connect the ray picture that we did in radiative transfer to this wave picture based on electromagnetic theory, classical electromagnetic theory. Okay. Now, I mean, from Fourier transform, some of these properties should be very clear to you. For example, if you have, right, so suppose, say, your electric field as a function of time looks like this, and it just is a pulse. There are no oscillations here, right? So if you take a Fourier transform of this, so this is like your, delta t, okay, and there is a DC value, right? If you have a signal which is always positive, the omega equal to 0 mode has the average under this curve. So this, the Fourier transform of this would look like, or power would look like. So this is ET versus T. This is C E hat omega squared, which is nothing but power in the Fourier space is nothing but this. And recall, for a real signal, this is always symmetric, right? Minus omega and plus omega have same power, but this is omega equal to 0, omega not equal to 0, right? This does not have any oscillation, so this is centered. Its power peaks at omega equal to 0, and it has a width, bandwidth. This is called bandwidth of order 1 by delta t. Okay. Similarly, if you have, these are just the examples. These are actually given in the book. Like if you have a finite, pulse. So 1, 2, 3, 1, 2, 3, 4. So one more. So if you have a pulse like this, that's 0 before this. So this is your ET versus T. If you take the Fourier transform of this, it should have 0 power at omega equal to 0, of course, because its average is 0, but it will be sort of peaked at omega naught, and it will have some sort of side bands here. So it's something like this. Okay, and of course at minus omega you'll have the same structure, but I'm not drawing that. And this delta omega has, so this is like your delta t. This is the pulse width. So this is like your 1 over delta t. In fact, you can actually try all this. I hope all of you know a little bit of Python or some other interpreted language like MATLAB. You can actually try these signals and look at the Fourier power and make sure that this intuitive picture is borne out by mathematics. Okay. Similarly, if you have a signal like which starts like this, sort of decays in time. There's not, so this is 0 at negative times. Okay, so this is time. This is ET. And this has some envelope which is a time scale delta t, right? Some time scale like an E-fold time or something like that. Then the Fourier spectrum or the power for this guy would be similar to, it will have blue. And it also again peaks at omega naught. This omega naught corresponds to this fast oscillation, pi by t. And it will have again a width which is going like 1 over delta t. Again, it's symmetric, so the negative minus omega naught will have the same. But we said, here we considered that we'll not consider the negative values of omega. We'll just have positive. We add all that power to here. Okay. So this is about a little bit about the Fourier picture or the frequency space picture and the real space picture of wave pulses, wave packets. The real signals are always wave packets. You never have an infinite wave, right? Any question on this? This is all actually given in Rybicki and Lightman, and you should read it. Okay, good. Oops. Where did I go? Give me a sec. Okay, so if not, I'll actually go to something else. So, okay, okay, now we will actually talk about polarization. Okay, polarization is a very, very important concept. Polarization and actually Stokes parameters. Stokes parameters are mathematical ways of characterizing polarization of a monochromatic light. Okay, so we'll consider monochromatic plane waves. Okay, so this monochromatic meaning single frequency omega, plane waves meaning it has the form e to the I k dot x minus omega t. Okay, so these waves are propagating along some direction k. Okay, now previously when we were talking, when I did this basic waves, I had this relation between E, K and B, and I had this, the direction of E was always perpendicular to the direction of K and B, and I took it to be, say, if K is along X, E is along Y and B is along Z axis. Okay, but so that those are like simple linearly polarized waves. So linearly polarized waves. But in general, you can have more complicated polarization of the wave. So if you have this direction of propagation, right, and if the electric field is always, so if this is like x hat, right, and your electric field is in y hat direction, and the magnetic field is out of this board, out of this whiteboard. Then, so this is B direction. So E and B will always be perpendicular. K will always be perpendicular to E and B. But the plane of polarization of electric field can actually rotate. So this plane can actually rotate in general. Or in other words, you have something called superposition principle, right? The wave equation is a linear equation. So if you have one solution, you can add up all the, a linear combination of all possible solutions is also a solution. So you can actually imagine a solution which is polarized along this direction and a solution which is polarized along this direction. Of course, each one of them will have their B's transverse. So the net B will always be transverse to E. But you can have more complicated waveforms. Okay. So in general, your electric field in vacuum will have, so electric field can actually be written as x hat. So yeah, sorry, this yeah, sorry, but this x, y, z, and now I'm actually taking my k vector along z hat direction. So, but I hope you are not confused. So let me just write down plus y hat E2. Okay. Times e to the minus I omega t. So what I'm actually doing here is I have fixed my position z. So let's say this is the z direction, x direction, y direction. So x, y, so it should form a triad, make sure that's true. So my wave is actually propagating in this direction, my k is along this direction. And I am actually sitting at some position, some z equals constant position, and I'm actually measuring my electric field in the xy plane. So it need not always be in x direction or y direction. It can actually, it will be in that plane. And this is the general form of the electric field that I measure at a given position. Okay. So it will have some component along x, some component along y, and these are the amplitudes of those. So in general, these are complex numbers because the x and y components can have a phase difference between them. Okay, and we can actually write it as E naught vector. This again is also a complex vector. E to the minus I omega t. So we are actually suppressing the space dependence, but looking at the time dependence at a given position in space, fixed position in space. Now, the point is we are looking, we are fixed in space and we are looking at how the electric field vector changes in time at that location where I am looking at. Okay, so let me actually write down. So since E1 is a complex number, we can write down E1 is equal to some epsilon 1 e to the I phi 1. So this is now real. This is a real number. Phi 1 is a real number, but E1 is complex. Similarly, E2, which is polarization along the y direction, amplitude along the y direction. This is amplitude along x direction. So it's epsilon 2 e to the I phi 2. Okay. So this is real amplitude and this is real phase. I mean, this is all complex analysis, complex numbers, simple complex numbers. Now we are interested in, so let me actually draw a figure. Oh, shoot. Just a sec. So okay, so this is my x, This is my y-axis, and now I want to trace out my electric field. How does my electric field looks like in this plane? Okay, so let me draw how this looks like. Let me just draw this figure first. This is actually an ellipse, I'm sorry for the bad drawing, but this is an ellipse. And these are the principal axes of the ellipse. So this is x prime, this is y prime. Principal axis means the axis along which the ellipse has the standard form, which is x prime squared by a squared plus y prime squared by b squared equal to 1. Okay, so this is the ellipse. So first let me draw it and I'll actually connect to it a bit. So this is the okay. So now this is epsilon 1, right? This is the amplitude, the maximum value of Ex is epsilon 1. Similarly, this is epsilon 2. The maximum value of Ey at any time is E2, epsilon 2. Okay, good. Okay, yeah, so this is x prime, this is y prime. Okay, so this is, this is the polarization plane that we are looking at. Okay, and in general, as I mentioned, a monochromatic plane wave will trace out an ellipse. So it's important to notice that this is monochromatic if omega is constant. Okay, so let's write down Ex. Ex is the electric field along x direction. This is nothing but epsilon 1 cos omega t minus phi 1. Just a sec, let me pull it up a little bit. Right, so recall there was this minus I omega t, so there is this minus I omega t, and E1 has e to the I. So the phase, including the time, is omega t minus phi 1, and this is basically a real. So we are taking the real part of this x hat component. So E1 e to the minus I omega t, which is epsilon 1 e to the minus I omega t minus phi 1. So that's the real part of this. So this is Ex, the electric field along the x direction. Similarly, Ey is equal to epsilon 2 cos omega t minus phi 2. Okay. Okay. Now we will have to use some trigonometric identity. So let me actually write down the answer first and then tell you how I got it. Is equal to cos omega t minus phi 2 times cos phi 1 minus phi 2 plus sine omega t minus phi 2 times sine phi 1 minus phi 2. What I did was I actually wrote this guy down as omega t minus phi 2 plus or just a second, or minus phi 2 minus phi 1 minus phi 2. Okay, I wrote this phase factor like this, and I just sort of expanded cos A minus B is equal to cos A cos B plus sin A sin B. Okay, so this is how I get this one, and of course we know that E y by epsilon 2 is equal to cos omega t minus phi 2. Okay. Now we want to eliminate omega t minus phi 2 from this from the relation between Ex and Ey, and you can actually see that omega t minus phi 2 is nicely appearing separately here. So how do we do that? If we do Ex by epsilon 1 squared plus Ey by epsilon 2 squared minus twice Ex Ey by epsilon 1 epsilon 2 cos phi 1 minus phi 2. So basically what I'm doing is I can actually so I can actually substitute this as Ey by epsilon 2, and I can actually substitute for this as 1 minus Ey squared by epsilon 2 squared. Right. If I do that and manipulate it, I get this equation. Okay. So we have Ex squared times some coefficient plus Ey squared times some coefficient plus some coefficient times Ex Ey equals a constant. So this has a form which is that of a, what do you call it, conic section, right? I mean ax squared plus by squared plus cxy equals d, right? Is a conic section, and if a, b, and c have certain properties, it becomes an ellipse. So let's see what that property is. So the determinant of these coefficients, so the coefficients of Ex Ey and Ex Ey are 1 by epsilon 1 squared minus cos phi 1 minus phi 2 divided by epsilon 1 epsilon 2 minus cos phi 1 minus phi 2 divided by epsilon 1 epsilon 2. I'm actually writing a matrix 1 by epsilon 2 squared, right? So this is the matrix of these coefficients, and in fact if you write it as Ex Ey, you can write the above equation as this: Ex Ey times this matrix times Ex Ey is equal to sine squared phi 1 minus phi 2. Right? You can see this is like it's a 1 by 2, this is 2 by 2, and this is 2 by 1 matrix. So in the end you get a number which is equal to that. Now this matrix, if it satisfies certain properties, that is, if the determinant of this matrix M, we can actually easily find that out, and this is equal to sine squared phi 1 minus phi 2 divided by epsilon 1 squared epsilon 2 squared. This determinant is always greater than 0, right? Because this is positive definite. So this means that this is an ellipse and not a general conic section, right? If the determinant of this matrix is greater than 0, you have an ellipse, right? You know this is a nice x squared by a squared plus y squared by b squared equals 1. This is the simple form of the ellipse when the ellipse is oriented along x y direction. Now you can actually see in this case the matrix will be 1 by a squared 1 by b squared 0 0. So the determinant is greater than 0. So what this means is that if the determinant is greater than 0, you can always transform this form of an ellipse into a form which is something like this. Okay. So this is called the, I mean, basically it's a transformation which takes you, you make a coordinate transform which takes you from xy to x prime y prime, and let's call this angle chi, right? So these are called principal axes. X prime y prime are called principal axes of the ellipse. Principal axes. Okay. Now, so so this is my claim that I can always rotate my axis such that the form of the ellipse becomes simpler. Okay. So this is a little bit of coordinate geometry and trigonometry. So if this angle is chi, we can actually see, right? So this now electric field now, so suppose you are at this location. This is your electric field vector, right? You can write the electric field vector either using x prime y prime or using xy, but the vector is the same, right? The components can change. Okay, so let's see. So ex prime, right? Ex prime is nothing but ex cos chi plus ey sin chi, right? I mean, I'm just sort of writing this x prime component, right, of electric field in terms of the x component and the y component. This is just like rotation of axis in some sense. Okay, and ey prime is equal to minus ex sin chi plus ey cos chi. Okay, so right, so what am I doing here? I'm just sort of saying that if my component of this electric field, for example, I don't want to make this very messy, but let me use a different color. So this is my ey and this is my ex. Okay, this point at that particular time is my ex and ey. Okay, in the lab, in the usual axes, and this is my, these are my axes in the primed frames, right? So this is my ex prime, this is my ey prime, this is my ex, and this is my ey. Okay, so just from basic vectors, this is clear, right? Ex cos chi, ex, right? So this, I mean, I'm just sort of rotating. I mean, this is just rotation of the components of a vector. Okay, good. And I also know that in the prime coordinates, my electric field should have a form like this: ex prime squared by epsilon 1 prime squared plus ey prime squared by epsilon.
So the prime framed is along the major and minor axis of the ellipse,
Yes.
right?
Yeah. Prime
Okay.
frame is along the principal axis of the ellipse.
Okay. Thank you.
Yes. This is equal to 1. So, I mean, since it's an ellipse, you can always choose a rotated axis in which your ellipse has a form like this, right? Like this. Now, so that's fine. So what it means is that we can always have ex prime is equal to, sorry, just a sec. Oh. Okay, so I can always have epsilon 1 prime is equal to just a sec. So Ex prime is equal to epsilon naught cos beta cos omega t, and Ey prime equals minus epsilon naught sine beta sine omega t, with epsilon 1 prime is equal to epsilon naught cos beta and epsilon 2 prime equal epsilon naught sine beta, right? So if I want to have this form satisfied at all times, I should be able to write this as cos squared omega t and this as sine squared omega t, right? Cos squared omega t plus sine squared omega t is equal to 1 at all times. So that means that this is Ex prime by epsilon naught cos beta, and this is Ey prime divided by minus epsilon naught sine beta. Okay, so you may have to actually think about this a little bit and work out on your own, but this is, my claim is you can always write this in this form. Okay, and this is a convention. This beta is this angle which relates, right? So the beta is this angle which relates the relationship between Ex prime and Ey prime. So basically, if you right, so if you take squared of this and add to this, so you have, yeah, so we'll actually come to that. So let me just, this is a claim, and I will show that this claim can be justified. And beta can have a value between pi by 2 and minus pi by 2. Basically, what you want to do is you want to be able to have, values of E2 prime to be between -1 and +1. And that this choice of beta allows that.
Sir, this is Kinjal. Can you explain the origin of beta and how, I mean, is it are we assuming it, or is it based on some math?
It's based on some maths. Basically the claim is you can always write it in this form.
Okay, okay. So we are assuming it, and then we are proving that it can ultimately be written.
Yes, yes, that's correct. So let me go back to the figure a bit. This figure is important. Just a sec. Right, so basically, so let me use a different color. Let me use red color. Okay, so so this is epsilon naught cos beta. The the major axis, the semi-major axis of this ellipse, right, is epsilon naught cos beta. That's nothing but this, right? This is the semi-major axis, and the semi-minor axis is minus, so epsilon naught sine beta. But the point is, I have chosen a negative sign here, so I'll just put an absolute value here to make sure that it's a number. Okay. And for negative, minus pi by 2 plus pi by 2, cos beta is always positive. So the point is, just a sec. Right. So beta, beta greater than 0 is clockwise motion of the polarization vector, right? So if beta is greater than 0, what do you get? You get, so let's say beta is pi by 4. So this is negative. So Ey prime is a negative number times sine omega t. So basically in that case, it will, the tip of the polarization vector will move in this direction, which is the clockwise. You can see the direction that I'm making, right? You can see the dot that.
Yeah.
Right. So this, right, if your beta is greater than 0, it's a clockwise rotation of the electric field vector. So this is clockwise, or R polarization, right circular, right polarization. And if beta is less than 0, then is anti-clockwise, or L polarization. It's actually easy to see. If this is beta is less than 0, then this is also positive, and then it sort of varies like that. This is just a convention, the sign of beta. Okay. Now what do we do now? Okay, so right, so from this figure, I want to have that figure here on the screen. Right, so from this figure, we can actually also write, so we can write the inverse relationship of this, right? We can actually write that Ex equals, this is, you can also do it through simple rotation matrix. Ex prime cos chi minus Ey prime sine chi, and Ey is equal to Ex prime sine chi plus Ey prime cos chi. Okay, so this is Ex and Ey, but we also know, we also know this form of Ex and Ey. So let me actually write that down. Right, so Ex, this is nothing but, if I substitute for Ex prime from here, right, I get epsilon naught cos chi cos beta cos omega t plus sine chi sine beta. I'm just substituting this sine omega t. Okay, so this is the first equation, and similarly this is equal to, but we know that the Ey is also can be written as epsilon naught sine chi cos beta cos omega t minus cos chi. I mean, this is just these relations that I'm writing down. Sine beta sine omega t. Okay, so this is my Ex and Ey in terms of epsilon naught and beta and chi. But we know that Ex itself actually is given here and Ey is given here. So so let me actually write that down. So Ex is equal to, it's just the expansion of this formula, is equal to epsilon 1 cos omega t. I'm just using cos A minus B formula, cos omega t cos phi 1. I'm basically expanding this. Cos omega t minus phi 1 is cos omega t cos phi 1 plus sine omega t sine phi 1 plus sine omega t sine phi 1. Similarly, Ey is equal to, let me create a little more space. Yeah, this is a little tedious mathematics, simple but not, but a little tedious. So I would actually recommend that you guys sort of work it out yourself. Epsilon 2 cos omega t cos phi 2 plus sine omega t sine phi 2. Okay. Now these are the forms that we have, and we can all we have to do is just compare this ex, this form of ex, and this form of ex, this form of ey, and this form of ey, right? So the coefficient of omega t should match, right? So cos omega t cos, so e naught cos beta cos chi should be equal to e1 cos phi 1. So let me write just by comparing these coefficients, comparing coefficients. What do we get? We get epsilon naught cos chi cos beta is equal to epsilon 1 cos phi 1, epsilon naught sine chi sine beta is equal to epsilon 1 sine phi 1. What else? Epsilon naught sine chi cos beta is equal to, this is from the third comparison, I guess, sine chi cos beta. This is equal to epsilon 2 cos phi 2. And the fourth relation is epsilon naught cos chi sine beta is equal to minus epsilon 2 sine phi 2. Okay, so what have these relations achieved? The relations, these relations have achieved, you can go from xy coordinate. So this is amplitude in xy coordinate, this is phase in xy coordinate, right? So you can go from xy coordinate parameters to the primed, the principal axis parameters, epsilon naught, chi, and beta. So what are the parameters? Epsilon 1 phi 1, epsilon 2 phi 2. Okay, so these are the parameters in the xy coordinates. From here, so you have four equations, so you have this, and what are the unknowns? The unknowns are epsilon naught, chi, and beta. So there are actually four equations and three unknowns. And the reason we have three unknowns is that there is a normalization condition that is satisfied. So you can always go from the quantities measured in the general coordinates to the principal axes of the ellipse. So this is very, very useful. And given epsilon 1 phi 1, epsilon 2 phi 2, the easiest way to express epsilon naught, chi, and beta is through something called Stokes parameters. Stokes. This is named after Gabriel Stokes of the Navier-Stokes fame. Parameters. So what is the time? Oops. So let me actually just write down the Stokes parameters and then end the class, because I don't want to do this whole mathematics again and again. So, okay, so let's see. So these are the Stokes parameters. Okay, so this is I square. So this is the first Stokes parameter. Sorry, not square. Oh, sorry. Okay. I is equal to, what do? I do epsilon 1 squared, the x amplitude plus y amplitude squared. So this is basically, if I sum this and this square and sum this and this, that's what I get. Epsilon 1 squared cos squared phi 1 plus epsilon 1 squared sine squared phi 1 is equal to epsilon naught squared. You can actually check that. Epsilon naught squared cos squared chi cos squared beta plus epsilon naught squared sine squared chi sine squared beta. That's from epsilon 1 squared. And similarly, epsilon 2 squared is epsilon naught squared sine squared chi cos squared beta. So you can actually check from these four, 1, 2, 3, 4, that you get the first relation, which this is called Stokes I. The second Stokes parameter is Q, Stokes Q. This is equal to epsilon 1 squared minus epsilon 2 squared. This is equal to, if we just do that, so epsilon 1 squared is just the addition of squared addition of this 1 and 2, and epsilon 2 squared is square addition of this and this, and you subtract the one from the other. What you will get is epsilon naught squared cos 2 beta cos 2 chi. Okay, similarly Stokes U is equal to twice epsilon 1 epsilon 2 cos phi 1 minus phi 2, and that is equal to epsilon naught squared cos twice beta sine twice chi, and this is the fourth Stokes parameter, which is equal to twice epsilon 1 epsilon 2 sine phi 1 minus phi 2. This is equal to epsilon naught squared sine 2 beta. In fact, you can actually derive it from these four equations. Okay, so this is a way. So you're given E1, you are basically given Ex as a function of time, for example. You have some, right? So you can measure this epsilon 1, right? You can measure phase phi 1 from this signal. So you know E1, epsilon 1 and phi 1. Similarly, you have some EY, which has some other phase, but same frequency, of course. Let me be careful. Same frequency means somewhere here. I'm sorry, but the frequency is the same. So from this wave, you can actually measure epsilon 2 and phi 2. So all these things are measured quantities. So you can actually calculate this and all these from your measurements of the polarized monochromatic wave. And once you have those, you can calculate your epsilon naught, you can calculate your chi's and so on. So these principal axis quantities are epsilon naught equals square root of I, right? And sine 2 beta is equal to V by I. This is simple, right? This is just a ratio of this and that will give you sine 2 beta. Similarly, tan 2 chi is equal to U by Q. Okay, so but from your lab frame quantities, from your general orientation, you have measured epsilon 1, phi 1, phi 2, and from after calculating I, Q, U, and V, just by using these relations, you are able to calculate epsilon naught, beta, and chi, everything that you needed in order to go from xy to x prime, y prime, the principal axes. Okay, the other thing that you can actually check is that I squared is equal to Q squared plus U squared. Just a second. Is I squared equals Q squared plus U squared plus V squared. U squared plus V squared. So this is the total intensity. So this is the fourth relation. So you have four equations, but they are not independent. If you If you combine them, this is the fourth relation that you get. So that's why you only have 3 real unknowns, even though you have 4 equations and 4 known quantities. Okay, so right, so this, let me just end finally with a figure. So this is, these are axes, okay, and this is V axis. So this is V from this Stokes V. This is Q axis, and this is U axis. So X, Y, Z. So this is equivalent of X, Y, and Z that we are familiar with, right? So Q squared plus U squared plus V squared is equal to I. So I is sort of like your, this is your I. This is like your spherical radial coordinate, right? And this is like a point, projected point in the XY plane. So, okay, so this angle is 2 chi. This angle, like your theta angle. So this is like your phi in spherical coordinates. This is your angle. This is like your latitude. So this is like, this is normally taken as theta, but this is like your 2 beta, right? So you can actually see these relations, right? V equals I sine 2 beta, right? So this is like a V, right? So this is sine 2 beta. This is like your spherical coordinates. So I lies on a sphere, because I square equals Q square plus U square plus V square. And that sphere is called Poincare sphere. Okay, and this Q, U, V are the axes of these Poincare spheres. So beta varies from minus pi by 4 to pi by 4. That you can actually see, because 2 beta goes from minus pi by 2 to plus pi by 2. So beta goes from minus pi by 4 to pi by 4. Chi goes from 0 to pi. Okay, so you can actually see when does this ellipse become a circle or a line and so on, right? So if chi is, say, right, so let's see, let's go back to the polarizations. So let me just mention something. So V equal to 0 is linear polarization. So what does linear polarization mean? Linear polarization means that beta, right? Linear polarization means that sine beta is actually 0, or beta is equal to 0. So beta equal to 0 in this figure means that you are in the QU plane. QU plane. Your I lies in the QU plane. Then you will have linear polarization. That is V equal to 0. Okay, you get it. Basically, beta is equal to 0. Similarly, V greater than 0 is R polarization, and V less than 0 is, of course, L polarization. That's easy to see. So V greater than 0 is beta greater than 0, and we sort of talked about it, that beta greater than 0 is clockwise polarization. Basically, what you're doing is you're looking towards the z-axis. So this is xy plane, and you are sort of seeing towards the minus z hat direction. The wave traveling in z hat direction is coming towards your eye, and then the sense of polarization is defined by that direction. Okay, so this is R polarization, L polarization. This Q by U, right? Q by U. What is Q by U? Q by U. Q by U gets your chi. This determines the orientation of the polarization ellipse. because it gets you the chi. Chi was this angle between the lab x-axis and the principal x prime axis. Okay. And so Q is equal to U is equal to 0. This corresponds to circular polarization. What is circular polarization? The minor and major axes are equal. So basically beta equals pi by 2. And you can actually see in this diagram, sorry, beta equals pi by 4. Pi by 4.
Pi by 4. Pi by 4.
Yes. Yeah. Because that's when your cos beta and sin beta are equal. Right. So these were the amplitudes. Right. So epsilon 1 prime and epsilon 2 prime, or epsilon naught cos beta and minus epsilon sin beta. When the amplitudes are equal in the principal directions, cos beta equals sin beta. That is tan beta equals 1. So beta is pi by 4. So beta pi by 4 means these poles, right? This pole and this pole. And these are the poles of this sphere. So these are circular polarization, corresponds to poles in Poincare sphere. So this is actually a nice way of looking at, I mean, all this mathematics sounds a little tedious, but once we are convinced of this, in the end, we really don't have to think too much. All you need to calculate is IQ, UV, you know whether it's linearly polarized, R circularly R polarized, L polarized, circular polarized. It's very, very simple. It becomes simple to talk about in terms of this IQ, UV, and this is also the standard terminology. Okay. So I encourage you to look at it in Rybicki and Lightman. This is a little tedious, but I encourage you to work it out on your own. Okay. So we'll end here, and this diagram is useful to remember. Any questions?
Sir, you have written at one place that beta varies from, minus pi by 4 to plus pi by 4, but it actually varies from pi to pi, right? Minus pi to pi. Minus pi by 2 to plus pi by 2.
This one?
Beta.
Just a sec. No, so this is like a spherical coordinate, right? So in this case, everything, all points on the sphere can be covered if beta goes from minus pi by 2 to plus pi by 2. So beta goes from minus pi by 4 to plus pi by 4. Earlier I had written beta going from minus pi by 2 to plus pi by 2. But it turns out that you only need this. Everything else actually can be mapped on this. Okay, so that's the idea. A priori we didn't know that, but when you sort of map it to spherical coordinates, you will realize that this is all you need to describe general monochromatic elliptically polarized light. Okay, so I will actually end here. If there are, so I'll stop sharing and I will stop recording. Sorry, I exceeded today by quite a bit, but this topic was a little tedious, so I didn't want to end.